Hello, I'm Xiaoqi. I'm a postdoc from University of Toronto. Today, I'm going to present our paper, Mechanism Design for Online Resource Allocation, a Unified Approach. So this is a joint work with Alberto from University of Toronto, Bo and Danny from HKUST, and Yuan from University of Macau. We are considering a general online resource allocation problem by positive pricing. We assume that there is a single type of resource with limited supply, and we normalize the total capacity to be 1. There is a supply cost function f, which models the cost of resource supply with respect to the total resources that have been allocated. And we consider there is a set of agents that each agent has a valuation Vn and resource requirement Rn. And also we assume that the value density, which is defined to be the ratio between the valuation and the resource requirement, is lower and upper bounded. So if we take an online knapsack problem as example, then the valuation and requirement of each agent can respectively denote the value and weight of each atom. So upon the arrival of a new agent, we have to make an online decision by publishing the price for this agent. And upon receiving the price, the agent will make a decision about whether to purchase or not the resource that he or she requires by checking whether the valuation Vn is going to be larger than or equal to the potential payment or not. And the target is trying to maximize the social welfare of the resource allocation, which is defined to be the aggregate total valuation minus the supply cost. So again, in this example, by considering the online knapsack problem, the supply cost function here can be used to model the efforts, let's say the owner of the knapsack needs to spend on carry the knapsack. So unlike traditional online resource allocation problems, here the most important difference is the explicit consideration of the supply cost function f. By considering the supply cost function f, we can use this model to consider many real-world resource allocation problems. For example, when we are considering the resource allocation in cloud computing, we can use the supply cost function to model the power consumption of a server with respect to the total CPU utilization. In compute networks, we can use F to model the delay as a function of the total throughput. In these two examples, we can see that the supply cost function F is usually strictly convex, meaning that they have an increase in marginal cost F prime. So this motivates us to focus on online resource allocation with strictly convex supply costs in the paper. To quantify whether an online algorithm is good or not, we adopt the standard competitive analysis framework by comparing the performance of an online algorithm to its offline counterpart. So in the offline setting, when we assume that all the arrival information of the arrival instance, which is defined to be a set A here, and we denote the optimal social welfare as S offline. And then in the online setting, what we need to do is to develop a positive price, PM, upon the arrival of each agent so that the competitive ratio, which is defined in such a manner, is bounded by a constant. So here, what I want to emphasize is that since we don't know the total number of agents, the competitive ratio alpha should be independent of the number of agents at the same time. And also, since we are considering a maximization problem, alpha is always larger than or equal to 1. And of course, the closer to 1, the better. So we need to design the positive price so that alpha is as close to 1 as possible. So in the paper, our idea is to design a pricing function phi, which maps the current total resource utilization Yn to a price Pn. In here, Yn represent the total resource utilization after processing agent N. So record that the online decision-making process is as follows. So if the valuation of this agent is larger than or equal to the potential payment, and then this agent gonna make the purchase. Otherwise, the agent will leave without making the purchase. So in this regard, for the first agent, we have to post the price P0. Therefore, we have to do some initialization here for the value of Y0 and P0. So as we mentioned at the beginning, the value density of all the agents are lower and upper bounded. So can we set the pricing function to be equal to the lower bound all the time? Or can we set the pricing function to be the maximal value density? Of course, we can do that. The problem is that if we set the pricing function 5 to be such a case, and then we are going to accept all the agents regardless of their value density until reaching the capacity limit, right? And for this design, we are going to accept those agents whose value density is P bar, otherwise we will reject them, right? So we can see that these two designs are either very conservative or very aggressive. So the question now is there any design sitting in between such that we can make the competitive ratio of the posted price mechanism as close to 1 as possible? In order to answer this question, let's talk about some design principles for the pricing function in a very high level. So principle number 1, we argue that we have to accept agents regardless of their value densities at the beginning up to a certain threshold omega. So this means that the pricing function must be equal to the P underbar when the total resource utilization Y is within a certain threshold. The reason here is because suppose the pricing function is not designed in such a way, let's say the pricing function is given by this curve, and then we can always prove based on the definition of the competitive ratio that the worst case competitive ratio of this pricing function will become unbounded. In fact, the proof here is very simple. By artificially construct a rival instance where in the value density of all the agents are always equal to the minimal, P underbar. And then in this case, in the offline setting, we are going to accept all the agents up to this threshold because all of them are profitable. But in the online setting, we are going to accept only the first agent, right? So the total social welfare will become this value. And then when we artificially set the resource requirement of the first agent to be very small, and then we can easily see that the competitive ratio here will become unbounded. So principle number 1, we have to accept all agents regardless of their value densities at the beginning. Principle number 2, we have to increase the price when fewer units are remaining. This is actually very intuitive since scarcity should lead to higher prices, which is a very common phenomenon in practice. So mathematically, this means that the pricing function 5 must be increasing in this segment. Principle number 3, we should sell the resource at a profitable price, meaning that the pricing function should always stay on top of the marginal cost function. So here, I will not show the proof of principle P2 and P3. In fact, they can be proved in a similar way as the first principle by showing that if these two principles are not respected, and then the competitive ratio of the pricing mechanism will either become very bad or unbounded. So based on these 3 design principles, we know that the pricing function that we need to design should be a piecewise function in such a way which consists of a flat segment and an increasing segment. And the design parameters that we should take care of is what is the value of this flat segment omega, and what is the pricing function in this increasing segment phi. So this is the key question we need to answer in order to have a good design of the posted price mechanism with a good performance in competitive ratio. As one of the major results in our paper, we proved that if the pricing mechanism is alpha competitive, the flat segment, which is the value of the omega, should satisfy these conditions. And if, let's say, the value of omega is chosen as a feasible value, and then the second condition is that the increasing segment, the pricing function in this segment should satisfy these conditions. So of course, we don't need to read these equations. They are basically derived by principled online parameter analysis. So this is the first major result that we provide in the paper. Based on these sufficient conditions, we prove that the optimal competitive ratio is given by this fraction. Here, the H function is defined as the convex conjugate function of the supply cost. So, which means that as long as the supply cost function is given, and then the H function is also given. We also prove that there exists a unique threshold omega and a unique pricing function phi, such that all pricing mechanism achieves this optimal competitive ratio. What I want to emphasize here is that the calculation of this optimal threshold omega depends on the cost function f, p underbar and p bar, which is independent of the total number of agents. And the second remark is that if you write these conditions in a more compact way as here, then we can see that the pricing function that we need to design is actually a nonlinear eigenfunction of this nonlinear eigenvalue problem, and the competitive ratio is the nonlinear eigenvalue of this problem. So in general, such problems cannot be solved in analytical forms. In the paper, we provide a very comprehensive numerical computation of the optimal competitive ratio and optimal pricing function. In fact, we can show that the computation of those key design parameters can be performed in 3 different cases, depending on the relationship between P bar, P underbar, and the minimal and maximal marginal cost. What I want to emphasize here is that in this talk, we only mention this case to illustrate the design philosophy and principles of our optimal pricing function design. For the second and third case, the idea is similar, but with some slight difference about the boundary conditions in this part. So the details of this case and this case are given in the appendix of our paper. A very interesting result here is that although in general, the optimal pricing function and the optimal competitive ratio cannot be given in analytic forms, as a special case, when the supply cost function f is 0 or linear, we do have the analytic solution for the pricing function and the optimal competitive ratio alpha. As we can see here, the optimal competitive ratio alpha is 1 plus log of this ratio. What I want to say here is that this logarithmic competitive ratio is actually not new, but one of the most important contributions of our paper is that we provide a unified approach to characterize the optimal competitive ratio for online resource allocation with either 0 supply cost or linear supply cost or strictly convex supply cost. And although for these 2 cases, the result have been reported by existing literature, such as 41 and 42 in our paper, the result regarding the general strictly convex supply cost case is new, which is the first time that such optimal competitive ratio has been obtained. So to show a better picture of what this optimal competitive ratio looks like, we did a case study in the paper when the supply cost function is quadratic. As we can see here, when the lower bound of the value density is 0.3, and even the upper bound of the value density is as large as 20 times of the lower bound, the optimal competitive ratio is still roughly around 2.7. So the result here is very positive. In conclusion, in this paper, we provide a unified approach to characterize the optimal competitive ratio for online resource allocation with supply cost. In the general case, when the supply cost function is strictly convex, we show that the result cannot be given in analytical forms. So we provide a computational method for the calculation of the optimal pricing function. Since the model here is very general, it can be extended to more complex settings by considering, for example, multiple knapsacks or multi-unit auctions and combinatorial auctions. I'm going to end my talk by briefly mentioning our current ongoing work. And if you have any question or comments regarding the talk and the paper, please feel free to contact me by this email. The slides and the full paper will be uploaded to my website. Thank you very much.